Progress.
Okay, so we're recording. And now share the screen. Okay, so we should be sharing. Yeah. All right. So as I was saying, so on Tuesday, as Brandon, right? Brandon said, we were basically comparing a deep neural network to CNNs, but actually we're going to make this a little bit more interesting and more fun, right? So what I was saying with machine learning is that a lot of things revolve around competition. And so you guys are going to compete against each other for this assignment, okay? So there will be only one A, and then everyone else will get a D who does not. No, I'm kidding. You'll get grades, but I will give you a little prize. I have like a 3D printed thing. So that'll be the trophy to whoever gets the highest score on this one. Okay? Do you see what I'm saying? It's not gonna be easy. But I think it'll show you exactly how things work. So we're actually going to mimic the 2012 breakthrough in machine learning. So I think I told you in 2012 there was a breakthrough where people finally found out about deep learning and those kinds of things. You see that? So we're basically mimicking that on the CIFAR10 data set. Okay. So I don't remember where we left off in the code, so we'll need to look at that. But basically, you'll have, the goal is very simple. Whoever gets the highest score wins the prize. And then obviously the grades, that's different. So we're gonna do that, and I'll discuss the code. So I think the best thing I can do probably right now is just start the environment and just see where I left off on Tuesday. Activate I-37 sensor flow. Okay. So let's go to Okay, so this should be the code that I was going through on Tuesday. All right, so CIFAR10, VNN, CNN. Okay, so let's start the Jupyter Notebook. And we're going to click on it. So let's kind of do a recap of where we were. So on Tuesday, we introduced, Keras. We talked about the data set, right? I conveniently got the data from CIFAR10. Now you will have an assignment, as we talked about, of getting your own data set and all of that. But I'm going to add something to that assignment, okay? And it's this part here, the competition, okay? Because obviously we can't have a competition with everyone using a different data set, right? So there's going to be now two parts to it. The one where you get your own data, but this in particular. All right, so I've given you all the code, but the code that you can use, or a lot of the code that you can use, but I haven't quite solved, all of it, okay? And so it's up to you guys to, just see how you can get the highest score. All right, so let's just restart the kernel here to clear output, and let's just start running. Okay, so I'm gonna run the library. So these were the Keras NumPy libraries. Okay, we've got 10 classes. We load the CIFAR10 data set, which is, I think, 50,000 samples for training, 10,000 for testing. And, we load them conveniently from the CIFAR10 library, from the keras.datasets module. Okay, remember, we normalize the data, right? So these are things that might, if you pay attention to them, might get you better results. Okay, then we printed out the shapes. All right, so then we looked at the value, for instance, of one of the samples. We converted it to categorical. Remember, this is called one-hot encoding. If you remember, we discussed that on Tuesday. You can see the one-hot encoded version of a label number 4. Okay, then we have the data there, 50,000 by 10 now for the Y. This one-hot encoded, and then our images were 32 by 32 by 3. Okay. So then we started thinking about how to solve this problem, right? And okay, so we didn't get that far. So what I told you guys is that initially I gave you the classic XOR problem, right? And in the classic XOR problem, you solved it with logistic regression, and then you solved it with a deep neural network, right? And you were able to solve it and fine. And you know how to do deep neural networks because of that. Then now I'm giving you a much more challenging data set, which is CIFAR10. You could argue this is comparable to the 2012 data set ImageNet, where they were trying to see who would get the best scores, okay? So it's somewhat comparable. All right, so that's a good thing. So and it's 50,000 samples. It's a good size, even though it's not technically considered big data. It's a good size, 50,000 and 10,000. Okay, so then you're going to solve this one. And that's really it. So how do we solve it? So we need to have, some kind of a neural network, right? So that's basically the idea. So what's the first thing that you can try? Well, you already know how to build neural networks with keras, right? Because you learned that from the XOR problem. The only thing I said is now we have higher level API and lower level API, right? So we have like this approach and the other approach. And then sequential is one approach. And then this is a more low level API approach that we tried and discussed on Tuesday. So how does this one work? Basically, this neural network has the input is 32 by 32 by 3, right? That's the images. Then we take that input. Notice it goes in here and it goes through this to become X. What do we do here? We flatten the vector, right? So we spaghettify it or flatten it, right? And that gives us a new shape. I think it was like 3,000, maybe something like that. Then that shape X goes into the next layer, right? Which is a dense layer. Now, the reason why we have to flatten it is that dense only takes flattened vectors, okay? So that's not a limitation, it's just a specific way of how it's set up. Then the network is 200 neurons, right? And that gives us X with a ReLU activation, yes? Then that X becomes the input to the next layer, which is it's a dense layer with 150 neurons, and it's got a ReLU activation, and that becomes X. And then finally, that X goes into the last layer, which is a dense layer of how many neurons? 10. Very good, 10. And the activation softmax because we want the values to add up to 1. Remember that? And that's kind of where we were. And then we set up the model. So I'm going to hit run. That's our model. We run the summary just to know the number of parameters. And we've got 646,000 parameters already in this model because it's a large image. You can see it is when we flatten it is 3072, and there's all the layers. Does this make sense, guys? Okay. So where are you here? When you built this neural network, you're probably the 2000s, I would say, somewhere around that. People could do this theoretically. All right. So you're not exactly in 2012 yet, is what I'm trying to say. Historically speaking, you haven't gotten to the competition. But imagine that you're one of the teams that decided to enter that competition in 2012. I forget what the conference is called, they created a challenge basically in machine learning. They always do this. And somebody had created a data set called ImageNet, and I believe it was 1.4 million images and 1,000 classes, 1,000 like bear, bird, car. And so really any team could go in, participate, right? They had to come up with a model and apply it to the test set and see who got the highest score. Do you guys see that? So you guys are a contestant or you know, a participant. You could show up with this model. See what I'm saying? And basically then see how you perform. So that we're going to start there. This is what you know from XOR. So I'm going to click on, we have the Atom Optimizer, right? That's what allows us to train with a learning rate of 0.005. And then we assign the optimizer here. And this is something that, you know, we haven't really discussed yet, but these are the loss functions. This is how, like the MSE and all of that. So these are the things that we use to optimize our problem, to compare the predicted to the real. Okay, that's basically what it is right now, what we're doing. Any questions with that? All right, so then we hit run, okay? And then here we're gonna do train, right? So we have X train, Y train, right? That's what we're trying to learn. We have the batch size, so that means we're giving it 32 images at a time. We're gonna do 10 epochs, and we shuffle the data every epoch. That means we like randomize it every epoch, okay? So this is the train part, so I'm gonna go ahead and run it. And there it is, it's training. Okay, and you can see what you want to look at is the loss function or the loss value, which we want to minimize, and the accuracy, which we want to go up. Okay, that's basically, so you're competing, and maybe if you get 99 here, you win, right? So that's kind of, well, it's doing this. Let me get the GitHub. Just copy. So yeah, so it's this section here. Okay. Back to it. All right, so it's still going. All right, the loss function is at 1.5. The accuracy is at 47. So maybe, right? Maybe we'll just win price. So I did 10 epochs. Now, obviously, you could do more epochs, right? Those are things that you could do. You could change the learning rate. You could change the batch size. So as you're doing this assignment, try it. I mean, who knows, right? You might be successful. I only tried 10 epochs here, and let's see where I get on this one. Now, remember also, you have to look at the performance of the train set and the test set. And really, the winner will be whoever gets the highest performance accuracy on the test set, okay? So that's an important one. So we're epoch 8. Now we're using a deep neural network, right? Very, had several layers, 2 layers. Now that's another thing you can change also in that deep neural net. You could add more layers, more neurons. There's a lot of things you can do. Okay, so let's give it a second. One more epoch to go. Any questions while it's doing this? No. So it's not looking too good, right? What's your interpretation of what you're seeing? About 50%, yeah. So even though it's deep learning, was not able to, 50% is not great. Do you guys see that? So what do?
UCN.
UCNNs, right? So we're gonna try CNNs, and basically, so this is again like how things advance, right? So the deep neural net didn't quite do it, but we want to look at some of the metrics. So let's take a look at evaluating, right? So I'm going to copy this. Okay, there it goes. And now this is what's important, how it performs on the test set, because the test set is not something that that data the model did not see. And so, this is, we want to see if it does well on the test set. So you can see the loss was 1.45 and the accuracy was 0.48 actually. So not so good. Okay. And here it just summarizes the values again, 0.48. So what else can we do? We want to visualize the data and everything. So I'm just going to run through this. I'm gonna, so I can visualize it. These are just the classes: airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. All right, so those are the 10 classes that we have there. Notice I'm going to use the model to predict on the X test and get the preds. Okay, so I'm not just evaluating, but now I'm predicting. Okay, and this is just so that we can visualize the data. Okay, we can take a look at the shape. Oops. Okay, so I'm gonna have to, yeah, so there's 10,000 right in there. But they're one hot encoded, correct? Because it says 10. Do you see that? So I'm just gonna I'm gonna change it back to with the argmax so I can get the actual value. All right. So if it's 0, 0, 0, 1, it's now a 4 or a 3. All right. So I'm gonna do that. Okay.
Can you go up a little bit?
Mm-hmm.
Can you go up a little bit?
Mm-hmm. And this is in the GitHub, so you can just get the code from there. All right. So yeah, so I'm just doing this, and then now we can print out the shape. And you can see it's now 10,000, but one column. Okay. Now the last part, this, I'm just going to copy this code. This is just to visualize, so it doesn't really have anything much to do with the model. Basically here I'm iterating right through some samples. Okay. I'm randomly selecting some indices. Okay. You could select more. Okay. Just so that so you can just copy this. So this gives us some images that we predicted, and the predicted label basically, and the actual label. So what's your interpretation of what you see? If the accuracy was about 50, then about half of these, right, should be correct, and the other half should be wrong. So it was a bird, it predicted a dog. It was an airplane, it predicted a frog. It was a truck, and it predicted a truck. Bird predicted frog, airplane predicted automobile, airplane predicted ship, frog, frog, cat, 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 ship, ship. You see that? So you can play with this code if you'd like, but most of it, you can just add more. This is just a way to show the prediction. Any questions on this part? All right, so if you think about it, what has happened? You used deep neural network and you only were able to achieve 50%. So that solution is not working. So now we're going to introduce the CNN, right? And the CNN is a much more complex architecture. I gave you the background on this on Tuesday, right? Remember the filters idea, guys? So I've already discussed that, right? So then we're just going to look at adding a CNN to our code. So I'll describe the architecture a little bit, but we can conveniently just use the Keras object for this. Okay, so
Do we know that, like, we know that the one hot encoder has some order? How do we know it's the same order as this? Or is that just testing or looking in the data?
okay, so if we look, so classes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Yeah.
Right. So your question is, how did we build this here? So we have 10. We selected some indices. And that indices then gave us the number probably from both the real and the predicted.
Yeah.
And then those numbers were just probably mapping to the classes. So this class is in here somewhere. We select 10 from the whole X test. Oh, that's what it is. Here. So we converted all here, we converted all preds already into the words.
Yes.
And then we just got them from there. So if you, yeah, so if we look at this, okay, we'll go through the code then. All right, so friends single. See, they're already the words, right? So any number that we had in there, 1, 4, 7, has already been mapped to the word itself. Okay, and we did that for both preds and for Y test. Okay, so they're both the same size, right? Okay. So then we have two arrays, pred single and actual single, which you can see here, right? Okay, so now so that, you know, let's say there's 10,000 indices and 10,000 indices. Okay, so then here, I will create a new thingy. Okay, and this is 10. So what we can do is print indices. Oh, did I mistake? You get it now or no?
My question is, if you change the classes array into a different order, airplane, automobile, bird, like you just switch them around, how do you know?
Oh, we knew this. We know that airplane is 0. Is that your question? Yeah, no, you have to know this. Probably in CIFAR10. Oh, I'm sorry. If that was your question, yeah. No, yeah. So I mean, obviously 0 has to be for airplane. How could we test this? Well, I could grab,
It makes sense from looking at the pictures. I didn't know where the order comes from, so.
yeah, so trying to think.
I think this is the data set. Like CIFAR10.
Does it appear somewhere? And
If you go to the website, and CIFAR10 in Google.
here. Does it show the label? Hmm? These are the labels, but how do we know the number? Yeah, the order. Okay, so 0, 1, 2. Yeah. Yeah, so it's got to be a fixed number for sure. Yeah. So that what I was gonna do is I was gonna run an airplane through the classifier, and we should get a 0. I mean, you guys understand? But yeah, those have to be fixed. Okay. Did I answer your question?
Yes.
All right. All right. Yeah, good question. Okay, so yeah, so I kind of went fast through this, I realized. But yeah, so we've got the labels here. Okay. We're selecting 10, just 10 test samples randomly. These are the IDs of them. Okay. And then we run those through the classifier. Okay. Or just view them basically, because we already have the predictions here, right, in Preds and Y test. Okay. So we ran the classifier here. Okay, so if we did, this is what I wanted to do. Copy this. Call it A. And X test, right? X test. What's the actual? This is airplane, right? Which should be 0. So that's the second one. So it should be 1814. Yeah. Okay, so then if I do 1814 here and print A, I would get the 1 hot encoded 0, which should be a 1 followed by all zeros in the vector, I think. Did it misclassify it? Oh, it did misclassify it. That's what it was. So it did misclassify it as frog, and frog is actually 0, 1, 2, 3, 4, 5, 6, right? So the 6th one, 0, 1, 2, 3, 4, 5, 6. Actually, it's saying that the highest is 23, which is automobile. Indices.
Well, isn't it just the
Huh?
different, we took different indices than the pictures? Because you created new ones. So it took different samples, you know what I'm saying? In the 23, you ran it and you got 10, but in 20, you ran it before that, where you have different ones.
When you say in 23, I have 10 here. But I'm getting the indices though.
Yeah, but you generated the same.
You mean that it's a different prediction? Not this.
Number 20.
Yeah.
it's a different generated. This one,
Mhm.
they're different, the indices are different, because we generated them once, then we generated them again in the one before. So we generated indices once there and have the output for them. However, then after that, we generated new indices in the space above that, in the code above. So these indices don't match the indices which we display.
So you're saying these are not in the same order?
We're taking 10 random samples from the X test, right?
Yeah, but it's these, right? These 10 here. Oh, yeah, because I'm running it again. Yeah. I see what you're saying now. You're right. Then we'll have, I see what you're saying. Yeah, you're absolutely right. Okay, so then now it should be frog, right? Is what you're saying.
No, we don't know the indice number.
We don't know the indice number, yeah. So then we have to print it, yeah. Okay, so yeah, you're right. Okay, so print like this, right? Okay, so okay. So now which one? Pick one. The third one, truck, right? Okay. So that should be 7991. Yeah. And truck is the last one. Okay. Truck 7991. Yep. Fingers crossed. Oh man. So -1, right? So this is -2, -3, -4. Yep. Got it? Guys, any questions? Any questions? All right, so we predicted a value, and that's hopefully that answers that question. So we have the labels, we predict, and we select the maximum value. Okay, so we run this, and again, we just get the results. Okay, so now the problem is that this was not very accurate at 0.50. So we want to throw in a new approach. So we want to improve our results by running a convolutional neural network. I'm going to change this. So hit run. All right. So we need to so what do we need to do? We need to go back to this step here. All right. And we need to redesign the neural network. All right, so instead of just being like this, which is one input layer, two hidden layers, and an output layer, now we need to have a new architecture. And so now you're going to learn to build a CNN. So we're going to go over here. Let's just copy the code so we don't have to type it up. And then I'll describe it. I'm going to go back here. Okay, so if you think about it, let's start with the easy parts, right? The easy parts are the input layer and the output layer. So this is the input, right? Which is the images, 32 by 32 by 3, right? Just for one image. Then if you notice, we have this, and you can think of that as just one layer. So if we go back to our example, here, like where we have one dense, right? Now we can replace one of those dense hidden layers with a CNN. a convolutional layer as they're called. So we go down here, and that's one of these. We'll need to talk a little bit about the parameters in here, but that's basically one. Then the second one we replace with this one. So this is like the second hidden layer, but now it's a convolution layer. Do you see that? Then the output of the second convolution layer goes into this, a flatten again. So we spaghettify it again, flatten it. That feeds into a dense, and this dense has 10 outputs. You guys see that? And then basically we once again build a model, and we just have to specify input and output. And that's a CNN basically. So let's talk a little bit about the details. So the input layer, it's a shape of 32 by 32 by 3. Because it goes directly into a convolutional layer, we don't have to flatten it anymore. Okay, the convolution layer is designed to be able to take a tensor like this one. Now, this input, since we're using we're not using the highest level API, we're using this approach where we get the input, and now the input plugs into the next layer. You guys see that? And that creates convolutional layer 1. Then convolutional layer 1, you can see it here, plugs in to the next layer to produce convolutional layer 2. Then we do flatten the convolutional layer 2 to produce the flattened layer, okay? And then this flattened layer goes into the last layer, the output layer, which is a dense layer of 10 units. And this one should look familiar to you because it is pretty much the same one that we had before, the softmax. If we compare it here, right? So this one is very similar. Does that make sense, guys? Does this make sense? All right, so we are basically replacing the architecture of the network, basically the two hidden layers with these two new convolutional layers. Remember, these are the ones where we have those filters, right? Remember, we talked about this on Tuesday. You have an image and you have a filter that's scanning through and modifying so it can produce other images, okay? So what are the parameters then? You can see basically this is straightforward, or at least a lot easier in Keras, because we can just use the convolution 2D function or object, okay? How many filters do we use? 10, right? You see that? You can define the number of filters. The kernel size is basically the size of the filter, right? So 4 by 4 for an image of 32 by 32. Strides is basically how it's skipping pixels, okay? So I think if I remember correctly, when it's 2, it's making it half the size. The output is half the size of the input. And if there's padding, because at the end, you know, you may have shapes that don't quite match, so you provide padding. In the second iteration, the second layer, convolutional layer, how many filters do we have? 20, okay? The kernel size is 3 by 3 instead of 4 by 4. And again, strides equal 2 and padding. Do you see this, guys? Does this make sense? So remember that the logic of this is that you have an image and you have a filter, right? The filter is running through the image. That's the convolution. So you can think of it as we give it the image of 32 by 32 by 3, and now at the end, we're going to have 10 versions of that image. And those 10 versions are the input to the next convolutional layer, where now we're going to have 20 outputs of that layer, right? So our input is whatever comes out of here and goes through this, and now we have 20 versions of it. The last part of it, that tensor that has 20 versions of the original image gets flattened into one single vector, and that's the input to the last layer, which has size of 10. Questions on this one? All right, so now, if you remember the filters, right? So these filters, what are the values of these filters currently? What's going to be the value of them? It's random, right? So that means we don't know what the filters contain, right? Those values, you know, it's not like when we did the passing a filter through an image, we actually had values, we knew them, a person created those. This time around, the way the CNN works is we define a filter of 4x4, but we don't have values in it yet. Instead, we initialize them randomly, but when we do the training, the CNN should learn those weights to fill in those values for the filters in the CNN. Okay, so basically we have our images go through here. They'll go to one convolutional layer, then a second convolutional layer, then it gets flattened and it goes into the output layer, the same softmax that we had before. So now I run this, okay? And that sets the architecture. And pretty much everything else is the same. So now we can take the summary. Okay. Okay, there's there is our architecture. Okay, so you can see the output. Notice how it's being reduced in size, right? So from 32 to 32 to 16 by 16. That's that stride that you saw. Then 8 by 8. And then the output of this gets flattened into 1280. And that goes into the last layer, which is 10. So which one do you think has more parameters? The deep neural network that we did before or the CNN? The DNN had more parameters. Does that surprise you? Maybe you thought a CNN would have had more parameters, right? And yet, so let's think about that one. We go over here. Parameters, it says for the deep neural network, 646,000. Parameters for the CNN, 15,000. Okay, so that defines it, right? Now let's go ahead. So again, going back to this idea of the competition, you guys now would say, well, they had a DNN, we have a CNN, you know, let's see how you do. So, okay, and that's the basic, actually, deep neural network architecture. Here's another one, which is a little bit more advanced, more complicated. And it's got a few things. So let's run the one we have. Okay, so we just have to copy this again, right? So the learning rate, 0.005, cross entropy. Okay. And now we're going to run this part here. It's not going to error out. And run. Okay, there it goes. So now we're using a CNN. What is the score to beat? 50, right? 50 accuracy. So we're up to 31. All right, so while it's doing this, because it's going to do 10 epochs of this, we can explore the other architecture. So I provided a second architecture just for contrast. Okay, so this is the one that I discussed, basically one input layer, two convolutional layers, and one output layer, the flattened layer, and then the output layer. So now let's look at this one. This is a deeper CNN. All right, so you guys, let's say this is, I give you this on the exam, and I ask you, tell me about this architecture. What would you say? Anyone? Yeah, please. It has 4 convolutional layers. Yes. And then what else? But you have to like imagine, draw the whole network, right? From input to output. So input is what? 32 by 32 by 3, because actually with CNNs, you can give it the tensors. You can actually give it, you know, it's actually 4 dimensions technically because there's the batch. So the batch could be 16 by 32 by 32 by 3. Got it? All right. Then 4 convolutional layers. And then how does it end here? Well, don't worry about that yet. So the dropout and the batch normalization, the leaky, all that, you can skip for now, but just tell me the architecture. Huh? Or convolutional layers, what follows that? It gets flattened, yes. Right, so there's one dense layer here and flat, so that's one. How many neurons in that one? 128. So think of it that way, right? Always in dimensions. Input of 32 by 32 by 3. Then the 4 convolutional layers, followed by a normal dense layer. So if you see the word dense, it's a layer, okay? Of size 128. Okay? And then and then the last layer is the output layer. So you have 10 classes. Does that make sense? Any questions on that one? All right, so convolution layers obviously are a little bit more complicated. This one has additional things that we'll have to talk about, right? We'll have to talk about some of these. So let's go back to the code. Okay, finished. So how did it do? 41, not so great. Actually worse, right? Okay, so that CNN didn't work. You trained it from scratch, 2 convolutional layers, but you still want to win the contest. So what do? Let's go ahead and try a deeper CNN. Do you agree? So let's try this one. So I'm going to copy paste this one. So we ran the previous one, and it actually did badly. Why do you think that is? Do you think it's just because it didn't have enough convolutional layers? I mean, that may be part of it. But actually, if you notice, this code here has these additional things. This thing called batch normalization. It's got dropout. So these are additional tools that we have available that, well, no, that over the years, people have discovered, okay, if we add this, you know, it's going to improve performance. You see that? So they're improvements to a neural network. Do you guys see how it's starting to get a little bit complex, right? All right, so, you know, so let's describe this architecture now, because we're going to run again. We're going to repeat what we did before, but with this second, deeper architecture. So this one starts at 32 by 32 by 3. The first convolutional layer has how many filters? 32. More filters. Do you see that? The stride is 3. Or sorry, the kernel size is 3 by 3. The stride is 1, right? So you can see that it's not 2 anymore. So it'll probably be the same size, I think, in the first layer. Here, the input, right, is shown here. So it goes in, and then it comes out of this. But now I have this additional thing that I've added called the batch normalization. Do you guys see that? So you already know what normalization is, correct? Normalization is, we did it already. You know, the values were 0 to 255, and we made them from 0 to 1, right? That improves. So we said that the inputs improve when we, or the models improve when we normalize the input data. Do you guys remember that? Okay, so I added some text here on batch normalization. So just like we normalized the inputs at the beginning, it has been found that normalizing outputs from one layer to the next as the model is learning is a good idea. Batch normalization does that. It calculates the mean and the standard deviation of the given batch and normalizes it. So what does that mean? It means that if you look at each convolution, right? If you remember the intuition, we give it an input image, we run it through some filters, we get what? The same image, but filtered, correct? So, but the problem is that image that comes out, that those additional images that come out of the convolution go into the next one. And then those produce other images and they go into the next one and so on, right? So in the past, CNNs that didn't normalize those outputs weren't doing so well, okay? And so now you add this step, batch normalization, which has a tendency to improve the model, okay? So if you notice, we are adding batch normalization after every convolution. Do you see this? So I have a convolution here, followed by batch normalization. Convolution here, followed by batch normalization. Convolution, and so on. So it's technically, you can imagine it as if we normalize the input images, we also normalize the output of every convolution. Any questions on that? Does this idea make sense? This just provides for a more stable neural network, okay? And then if you notice, after normalizing them, we are running them through an activation, a ReLU. But the leaky ReLU that we talked about. Do you remember that I just said the leaky ReLU, the only difference between leaky ReLU and ReLU is that it doesn't give you 0. Instead, it gives you a very tiny, like 0.00 something, 1 number, but not a 0, okay? Now, you might ask, okay, but how was I supposed to know to create this architecture, right? That might be the thing that you want to know, like the theorem that says you should have done this. There is no theorem. This is purely experimental. This is why I said you're all competing against each other, right? And so those of you that don't use batch normalization and leaky ReLU would probably not win the contest. It's kind of how it is. But the intuition is, as I said, every output of if you notice in the previous one, we didn't do any of this, right? Notice we had a convolution followed by another convolution, no batch normalization in between, right? And this idea is the idea that I told you guys before. The models start to become unstable. Why? Because they start to become deeper. You see that? So if you multiply 0.5 times 0.5, what do you get? 0.25. If you multiply, in the next time, if you multiply 0.25 times 0.25, what do you get? Smaller one, right? You see that? And eventually it can start to get unstable because it's getting deeper and deeper and deeper and deeper, okay? And so that's the idea, that it's a good practice to do these things to obtain better results. Any questions about this? Making sense? All right, so now we've specified batch normalization, leaky ReLU. We get the final output of the 4th convolution. So this is like 4 layers of convolution. And we take that. Oh, what? Continue recording. So let me just get my chart. Okay, so yeah. So we do the 4 convolutions, right? And we get the final set of images. Now we flatten it and we load it into a dense layer of 128, correct? What do we do again? Batch normalization. So what's basically the recommendation here? Whenever you're building an architecture from scratch, Maybe throw batch normalization after everything. You see what I'm saying? I can't give you like theoretical things. These are experimental things that people over time have learned. It's like they were stuck, things were not good, and somebody said, what if we do this? They did it and it worked. And then you kind of start to understand, okay, yeah, normalizing between layers works. They also ran a leaky ReLU, right? And then what is this one? Dropout. Notice there's one more thing called dropout. What do you think that is? It randomly disconnects. So remember that the neural nets here are fully connected, right? Every neuron is connected to all the following neurons in the next layer. But this was invented by Geoffrey Hinton, same guy of gradient descent from University of Toronto, and his team. And basically, if you notice, you provide a kind of a probability of 0.5. So you're saying basically that every epoch that you're running disconnect about 50% of the neurons, and learn the weights that way. And then in the next one, randomly disconnect another 50% of the neurons and learn the weights. Okay, so you're not always updating all the weights in this case. And the idea with this is that you're trying to prevent the model from always going, maybe just focusing on one section of the neural network and ignoring other sections. Because you're doing this of disconnecting. If it was focusing too much on one section by this, maybe when you do this during an iteration, right, it's not going to be able to focus on that area because the neurons are disconnected. So you're forcing the model to focus on other neurons. You see what I'm saying, guys? Any questions about that idea of dropout? And so the idea with this is in essence, it prevents overfitting, right? Or reduces it, let's say. Another way of thinking about this is that instead of you trying 20 different architectures by using dropout itself is trying different architectures. Because think about it, you're trying neural nets that are not fully connected anymore. So in one iteration, some neurons are connected, others aren't. And the next one, it changes and it keeps doing that. All right. So anyway, we can come back to these ideas, but basically, if you notice, for this CNN is different from this CNN, not just because it has more convolutions, but because it also has additional improvements like the batch normalization, the leaky ReLU, and dropout. Okay, but it is deeper. Now, this model, we're going to train from scratch. So that means that these filters that we're specifying, the 32, 32, 64, 64, notice we did provide more filters now, which have sizes of 3 by 3. Initially, the values are random. And during training, this is what we're going to learn. Okay? All right, so finally, we get from the dense layer of 128, we go to the output layer of 10 classes. We run again through an activation of, which is softmax, and basically we set up the model. Okay, any questions? Crystal clear? Okay. So I'm going to save it. I specify that architecture. Now we can run this again. So now going back to the story, you guys are at the competition, right? And then one team tried the CNN, didn't work. You guys come in with your own entry. Let's do the summary. So this is your model. See, much deeper, right? A lot more information going on. 592,000 parameters. So if we compare this to the original DNN, how many parameters did that one have? 646. So this one's still a little bit under. Okay, what else do we need? So now we can proceed to specify the optimizer. So the atom optimizer, the learning rate is 0.005, categorical cross entropy, which we need when we have more than 2 classes. Let's do that. And then now we're going to train it. What do you think will happen? We don't know, right? We have to run the experiment. So let's go ahead. It's training, it's learning from scratch. The accuracy is at 25. Ooh, it's going nice. Okay, while it's doing that, gotta wait. Any questions, I guess, while we're waiting? I mean, did you guys get it? I mean, did you guys get the idea of CNNs? It's a complicated topic, actually. So if you got it in 5 minutes, I mean, that's impressive. So 36, 37. So this is literally what has been happening. So as you can see, we started with a very simple DNN. Hopefully that's pretty easy to understand. Then we added convolutional layer, but without those little optimizations. Right? Dropout. Jeffrey Hinton wrote a paper for that, and it's in the GitHub, so you can read it if you'd like. The batch normalization, that's a big deal. And so over time, there's things that get done, right? There's another technique called residuals. That one's not being used here, but it was invented later, right? And these are just little things that they do to the networks that help them to learn better. 41. What's the number to beat? 50. Okay, so while it's doing that, I guess I can talk a little bit about the Jupyter. So notice that after it's doing this, don't look at the results. After we do the training, I have this line of code here. Model layers get weights, layer 5. So these are the weights. This is actually, when it finishes training, you can get the weights that you want. This is the thing that has a lot of value, because let's say that, Brandon, right? You build this same architecture and you have a GPU, right? And let's say this would take 2 weeks to train. So when you run it on your GPU, you run it for 2 weeks, and now you have these weights fully trained. And then everyone else in the class doesn't have a GPU, but they know the architecture that you use because they just copied this code. So what can you do? You can just share these weights with everyone. Everyone can just load these weights, and now you have the exact same model that Brandon has. Do you guys see that? How that works? So basically, what is that called? That is called transfer learning. Okay, and you can access these weights. If you want the weights for the first layer, layer 0, right? Next layer, layer 1, layer 2, layer 3, and so on. Okay, you can, here I just printed them out. They're just basically an array, but we did something like, when we exported that .h5 file, right? That's the same idea. You're basically can share the weights, or you can look at them, etc. 57, you see this? So it's doing better. It's but if you notice, it's slower, right? And that's because, look at it, it's a very deep neural network. So this is why, so you can see, imagine if you were training on, we're only training on 50,000 images. Imagine if you guys were training on 2 million images, right? It would be, and it was a much deeper neural network, much deeper CNN, then obviously it would take longer. This is where now we really want to have a GPU. In fact, for this homework assignment, I'm pretty sure you're going to wish you had a GPU. Because it's, oh, you do have a GPU, yeah. So he has Brandon, you have an advantage over everyone else. Really? So you're done already? What's your highest score? 83. That's tough. Yeah, that's okay. Yeah, that's what I was gonna say. You're what do you have? You have a 3090. Yeah, see, I can't help to see this as an analogy of real life, because you're basically Meta or Google or Nvidia, and you guys are just me trying to compete, right? This is the reality of it. If you want to go to one of these competitions, I didn't get 83 on this. I got 71, and I didn't have time to run 8 iterations of it because it was, it's taking a while. Yeah. So yeah, I don't know. Brandon, you may be the winner, but but guys, you got to beat that 83. Okay. Anyway, that it should be fun, I think. But yeah, I do. It does help to have a GPU. I can tell you, and not just one GPU actually, because Nvidia doesn't have a computer of just one, or Google or Meta of just one GPU. They have computers that have 10 GPUs, and then that computer is connected to another computer that has 10 GPUs, and they have a cluster of computers. So they end up having so many. I think if you look at Nvidia's the keynote, the conference, the Nvidia conference is happening this week. And if you look at the new products they had, it's a whole data center of GPUs. So you can probably have, like, I don't know. A cloud? Is that how much? Yeah, no, it's like a cloud, right? Yeah. Yeah. I don't know. No, right. Of course, it makes sense. I think I have a GPU, you have a GPU, I have a GPU, and I only have one. And I think I'm not entirely sure if I'm gonna be buying another one, or I'm just gonna go into the cloud, because it may become impossible at some point to do any of this with just one GPU. And I can't have a machine that has 4, right? I mean, I gotta eat. So it's not really, it's a challenge, unfortunately. But I'll show you today a little trick, right? So we're not done yet. I'm just waiting for this thing to finish. There's one more piece to this story. Okay, so let me just see where we are. All right, it's still going, actually, but good sign. We're up to 64%. We were at 50, and now we're at 64. So certainly, do you guys see that the CNN can give you an improvement? Okay, good. All right, now, while since it's running pretty slowly, actually, let's go. So I already talked about the weights, right? And I said, Brandon could do the nice service of just training this for all of us, posting it, and then you guys can download it, right, and use it. So that's how you would do it here. And then we're going to evaluate it, of course. I'm just repeating the same thing, right? Running the test set, running the classes. You're going to do all of this. And basically now you're going to get more correct classifications. Okay, guys? All right. So we already know that he got 83. So let's assume that's kind of where, make a note that that's what you can get with this CNN. However, there's one last piece to this story. And that is this section over here, pre-trained models. Okay, so that's what the last part of it, which you guys, I expect you to use this in your competition. And so now I'm saying you have 2 options. Okay, so currently, let's say that it's pre-2012, right? The last year, 2011, Brandon came in with this CNN, right? With all these. He trained it from scratch, right? And achieved 83%, right? However, there's another approach, pre-trained models. And a pre-trained model is that nowadays, let's say that I'm picking on you, but you grab that model and you just make it available. And now everyone can just download that model, fit it into their network, and process. So that means you have the weights that you train and you can just use them. All right, so Keras actually conveniently provides this module here called Keras Applications. And from it, we can import pre-trained models, the best, in fact. These are the best pre-trained models available. If you click on this, in this link here, this is a history of kind of the best pre-trained models available. So AlexNet, this is the one that won the 2012 competition, okay? VGGNet, ResNet, and something called Inception. Okay, so you can, to win this challenge, you can try any of these. All right, I provided an example here of how to call the VGG.net from Keras and also the ResNet from Keras. So I only gave you one example of how to use the VGGNet. But these are now models that have a defined architecture and they already have weights, okay? You don't have to define that architecture from scratch. So I'll let you guys read through this, right? It explains AlexNet in a lot of detail. It explains VGGNet in a lot of detail. And it explains ResNet in a lot of detail, okay? It provides all the improvements. You can see ResNet has some additional improvements. Now, do I expect you to tell me everything about these? No. At this point, it starts to get pretty complex. Okay, so let's go back to our code. So where we were, right, we defined this architecture from scratch, right? And it had one input, 4 convolutional layers, 1 fully connected layer, and an output layer, right? And you trained it from scratch. Now and we are able to get 83% accuracy. But, you know, the prize is $1 million or something. So obviously, whoever gets more than 83 in accuracy is going to be the winner, right? So that's your objective. So what do? So then what you can do is you go for these pre-trained models. VGG16 has, I believe, 16 convolutional layers. You see that? Whereas the one we defined from scratch had 4. This one has now 16. It doesn't make sense at this point for you to create 16 layers, right? Instead, you're just going to use those 16 layers provided in VG16 and add them onto your own network, okay? But the advantage of this is that you can actually import the weights as well if you want. So you don't have to train all these weights again. Now, keep in mind, because it's a longer network, if you were training all these weights, it would take even longer and you would need a GPU, okay? So let's see how this works, okay? So pre-trained models, and also, by the way, I provided this link. If you click on it, it just has, you know, all the examples of how to, from Keras, grab all these individual networks. So the way that it works is you do from Keras applications.vgg16 import VGG16. So now you can grab that pre-trained architecture, or you can do from Keras applications ResNet import ResNet 50. Okay, so these are 2 pre-trained models. Then here's a simple example of how you integrate it. You just invoke, for instance, the sequential and then sequential, right? And you add VGG16. Do you see that? So you can do it like this. So this just shows an example. Notice how many parameters it has. How many parameters does it have? 138 million. Right, so it's a lot of parameters, right? So here's the configuration. You initialize VG16. You specify the input size. It's the same one, right? 32 by 32 by 3. But now there's this included in it. So the VGG16 is trained to take an image and predict a class, 1 out of 1,000 classes. Okay, so maybe I'm gonna Don't have the tablet, but I'm gonna need to do this with the tablet. Since this is really important. We're focusing on this part of the code here where it says include top equal false. Okay. So let's switch to the whiteboard. Okay. Okay, so VGG 16. Let's say it has 16 convolutions. So there's the image, right? It's 32 by 32 by 3. And then it goes in here. Dot, dot, dot. And these are 16 convolutional layers. Then it has a fully connected layer, they usually do. And then it has an output layer, which this one is probably, although it's not up to scale, is 1 to 1,000, let's say. So it's already designed to predict things. You guys see that? If you leave that the top to true, it's gonna use this layer. But obviously we don't want that, right? Because how many classes do we have for this problem that you're tackling today? 10, right? We have those 10 classes that we talked about. So we give it images and we wanted to predict those 10 classes. So when we do that remove top true or whatever it was, what we're effectively doing is we're getting rid of the last layer. Do you see that? And instead, we're going to replace it with our own of size 10. Does that make sense? That's effectively what we're doing. So maybe for more clearness, I'm going to change color. And so you're removing the one that's provided and you're using a new one that you're going to define. So we copy this whole part of the network, okay? We copy this whole part of the network, but we're gonna replace, well, we defined that and we're gonna replace that because we're predicting a different kind of thing. You know, maybe you're predicting, I don't know, cars, right? Different model cars. So then you would use a different output layer, not the one that's given. Another thing is, because it's a pre-trained model with 16 layers, we have the option of keeping these weights or retraining these weights. Do you guys see that? So we have that option. This is your challenge. You're going to have to play with this to beat Brandon and his 83%, right? And so you're going to have to figure this out. All right, so hopefully that is clear enough. So let's go back to, let me stop sharing now. No. Okay, so again, so here then, I'll repeat, from Keras in this new approach, right? From Keras applications, we have the option of bringing in a pre-trained model. VGG16, which is the example I provided, But I also stress that there are other ones that you can try. In fact, ResNet is supposed to be better than VGG. I'll let you know that. Okay. So I that's why I didn't do ResNet, to see if you guys would figure out. So ResNet 50. Okay. ResNet 50, I believe, has 150 layers, 150 convolutional layers. Okay. That's a lot. All right. So then we can start here. I'll explain how this works. So now let's say that you imported VGG 16, that you decided you're going to go with that one, right? So you do this, then you have to initialize it. So you say include top equal false. What does that mean? That the last layer you're going to define now. Okay, you're not going to use the one that's provided. You're just removing it. You define here the input, which is 32 by 32 by 3. Now you have this piece of code here, freezing the layers. All right, so I wrote a little comment here. If similar images, you can freeze the network. Otherwise, common practice is to freeze only the top layers. Okay? Any questions about that? So what do you think so this was trained on something called ImageNet, which is a data set of birds, cars, buses. And then what are we predicting? Birds, cars, buses, right? So I ask you the question, should you freeze the layers or unfreeze the layers? Which means if you freeze the layers, it means that the weights remain. You're basically going to use the weights that they provided for you. If you unfreeze the layers, that means that as you start training, you're going to update everything. Freeze them. Why? Because they're similar, right? Also, I would say start with frozen layers because otherwise it takes longer to process because you're updating. You have to update all the weights, right? So that means you go forward and then you need to backprop 16 or however many layers you have. It's going to take you even longer. But if you freeze the layers, you're only updating the last layer. So it's going to be faster. Do you guys understand this concept? Any questions? Yeah. Huh? Just one epic or what do you mean once? What do you mean by that?
So instead of they train on the
you can try it. I mean, it's a good question. The thing that will answer that question is basically the performance. So, but I see what you're saying. So you're basically saying don't freeze the layers and train it. That's kind of what you're telling me, I think.
Yes.
Yeah. But what you're saying is, I mean, why would you freeze it? You only freeze them when you're gonna train. So they're already frozen. You're telling me you're gonna unfreeze them, train, and then use it to predict, correct? But so the concept of freezing just relates to training, not to inference. And you're telling me you're gonna unfreeze it, train, and then do freeze them and do inference.
So if we freeze the layers, the weights they got when training on theirs.
Yes, if you freeze them, like here, for instance, I'm showing you the code on how to freeze the layers, right? So it basically means that if I go back to this, right? When you're doing training, because you're going to feed it 15,000 of your own images to predict your own 10 classes. Remember that we've removed that top layer. So what's happening during training, all these epics, is that the weights in these red sections are not being updated. They're frozen. And only we're updating these weights here. The weights that go from here to here to do the predictions. Do you see that? But if you unfreeze the weights, then you're gonna update all of these. Yeah or no?
Would you? So what I was thinking.
You want to add more, like you want to use their pre-trained, but add 4 CNN layers and basic. You can do that. I'm going to show you how you can do it. So certainly if you want to beat Brandon, you might want to try that, but you're starting to get very close to GPU territory. Just keep that in mind. And yeah, and so that's going to be hours of training. Leave it overnight, probably. Yeah, sorry. But it's a lesson you got to learn of how this is. But the beauty of pre-train though is that if you freeze these layers, then it's way faster. And you already have 16 convolutional layers. Because remember the intuition of what I told you guys. You give it an image, you run it through 32 filters, you get 32 versions of the original image. This VGG was trained on millions of images. So it knows how to take edges and detect lines, detect curves. It knows how to get the basic stuff. You know what I mean? And the thing that sometimes for me is actually odd is that if you read the recommendation I gave you, if the images are very different, you freeze the last layers, but unfreeze the beginning layer. I would have thought it's the other way around, but it's actually because I guess these are capturing like higher concepts, right? Like these capture maybe eyes already or hair, but because you're giving it your images, you want it. I would say the intuition is that these first layers are going from pixels to curves and shapes, general shapes, and then these layers can grab a hold of those shapes and predict wheels if it's cars, or eyes if it's people, or clouds if it's the sky, something like that. Yes, please.
So basically, like we need to appreciate.
Yes. You don't. No. It's a. You see, if you freeze all of them, then you're not going to update them. But because you have a new problem, right? You definitely need to update the last layers of your output. Right. If you decide like the previous one, the one that's currently still running, right? Those 4 convolutions, we build that model from scratch. So our weights were random initially. But eventually we trained it and Brandon got 83. I got 71. And so those are learned from scratch. Pre-trained models, we can use the weights. Yes. Yes. You freeze the pre-trained ones, but you still need to train on the ones that you add. Yes. That's exactly what I'm going to show you right now. Okay. So we can finish this. Any other questions? All right. So let's take a look. So hopefully this makes sense. Let me switch over to here. All right, so let's once again kind of a recap. So you're at, I think, where is this? It's still running. It's still running, but I'm at 78%. You can see it's currently on Epic 10, almost done, and I'm at 78%. Yeah, it's still going, right? This is only, as I said, 4 convolutional layers and 1 fully connected layer. All right, but you want to try something else. So let's look at the Jupiter. Remember, I gave you this idea of the weight. So you decide you're going to use pre-trained models, okay? So here's the history again. Remember, ResNet is better than VGGs in theory. So that's for you. And you can find from the Keras API applications, you can figure out how to get them. Here, I just provided a simple example. So from Keras applications.resnet, import ResNet 50. Although the example I'm discussing here is for the VGG. VGG is pretty much like second place to ResNet. So you can see here, the way that it works is you initialize VGG. Okay, guys? You say include top equal false. That removes that last layer. you specify the input, which is 32 by 32 by 3. Okay, that'll work for your images. Then freezing the layers. I provided several examples here of how you can do this. Okay, so in this example, for instance, this is how you freeze them. It's very simple in Keras. You just say for layer in VGG.layers, and then you iterate through all the layers. You just grab layer.trainable and you set it to false. Does that make sense? Guys? That's it. Now, let's say that that doesn't work and you want to maybe just freeze the top layers, but the first 10 layers you want to train, right? So in that case, what do? You can do 4 layer and VGG layers and just slice whichever ones you want. So 0 is the first layer, obviously, right? And so from 0 here, we are going to, you can, so you can decide how you want to do it, okay? Now to check that it worked, you can iterate through this and you can say this second for loop is just so that we can print this out, okay? Just so that you can confirm which layers you froze and which layers you didn't. So actually these are all the layers from beginning to end, right? So you can do 4 layer in VGG.layers, right? And now just basically print them. So all of these here are what? Frozen. Very good. Frozen. Because we set trainable to false. So it's not trainable, therefore we cannot update the weights. Got it? But by default, they can be updated. Just keep that in mind, because when you're first doing this, you might think, oh, I'm just gonna, and it works. But actually, if you don't do this, you're gonna update them and you'll notice that it's taking longer, right? Because you're updating all the layers, all the weights. So I do recommend that you run this first, because that way, when you do the training, you're only training that last bit of it and you're using the weights in the beginning and you want to see if it works. Got it? Any questions? All right, once you've done that, then the last part is you want to build the architecture, right? And let me actually just connect this again. So you can see I wrote it here. You can see it's pretty simple. You just invoke sequential again, which is something you know how to use from the XOR lab. And you add VGG first. Remember that here in sequential, we just need to add the layers, right? So we add VGG. That's literally this one, right? We add that, the whole thing. We already told it that we wanted to freeze the layers. And so we just add it here. Because it doesn't have that last layer, we need to add that in, right? Our new last layer. So what do? The output from VGG, which is a tensor, what do? We flatten it, spaghettify it. And then connect that to what? A dense layer, a fully connected layer. How many neurons does that layer have? 10. What activation does it have? Why? Because it's usually what we put in the last layer. And that's it. Your architecture is done. See how easy that is? You just learn how to take a pre-trained model, freeze the weights or unfreeze the weights, and you can add however many things you want. So you wanted to add more layers, correct? So this is where you do it. Like, I guess here. So if you want CNN layers, you would probably do it here, actually. Right? Because this is CNN, and we flatten it when it goes into a dense. But since you want, let's say that you wanted to add exactly these 4, right? So then you could do that. You could, from the VGG, which is a CNN tensor, shape tensor, you would add your own CNN layers. Then the output of those layers you flatten, and then that flattened thing gets connected to the final dense layer. And that's it. Notice how easy that is? Any questions, guys? All right, and then finally, so here you can do the summary. You'll see notice it has 14 million parameters. You do the same again. Set up the atom optimizer. Notice my learning rate here is not 0.0005. The reason I actually think that 0.0005, the learning rate that we're using in the previous examples, is a good one. The problem, it was taking a very long time. And I was doing this afternoon on this laptop. And that, you know, it doesn't have a GPU. So I wanted to get something going. And so I made the change of the learning rate to, where is it? To 0.001, but I added a comment there that I actually think 0.0005 is better, just slower. Okay. And then here's the, notice also another thing I did is I made the batch size 128 instead of 32. That's just to speed it up again a little bit. But 32 is fine. I also only did 4 epochs just so I could get some result. At the end, I only was able to reach 0.55. So actually the from scratch CNN has achieved 83. Do you see that? But I'm saying I only did this to complete the pipeline. I didn't have enough time to really like try. However, what I'm saying is now you have a whole bunch of options. And let's see who gets 100%. Yeah, so that's it. I mean, that's the challenge. Okay, and oh yeah. But have you used the pre-trained model? Okay, you have. So with the CNN, you mean?
Correct. Yeah.
The from scratch CNN, you're at 83. Yeah, this is still running, I think. Oh, it finished. So I was able to get 83. Oh, let's see on the evaluate. Yeah. Really? Okay, so this, let me see what I get. So this is, because I was only able to get 70 before. So you ran this, correct? $71 I get actually. And you got how much here?
We're changing the architecture 80.832.
83. We're changing what part of the architecture? Here? In this? From scratch, you just added more layers. Okay, how many layers did you add?
5, 6, 7.
So you added 3 more. Ended up with 7. Okay, and you trained it from scratch. You had to drop out in a few places. Yeah. Okay, and your test was 92. Your 92 and 83. So those are the values to beat. Yeah, that's it. So 92 on train and 83 on test, correct? This is the number to beat. So he already told you, you should have kept it a secret, that if you add 3 more layers to the from scratch model, you can achieve this. Okay, so you guys definitely do that, right? But I am giving you, in theory, what I am giving you here with the pre-trained models should do even better. Okay, because ResNet, as I said, has 150 layers. Trained on, I don't know, 10 million images. And if you freeze them, then it knows how to take an input image and find patterns. And then hopefully that. So anyway, I mean, that's basically how competitions work. So this is what, so I took you now to basically 2014. So that's kind of where you are in terms of what you know, what the tools that you have for machine learning. I mean, there's additional things, obviously. But yeah, so any questions? Everything's clear? All right. All right, so a few reminders. Please remember that exam 2 is Tuesday, okay? and it'll cover everything up until what we covered today. And then, yeah, work on this, obviously, because you have the exam. This homework will not be due a week from today. Instead, it probably will be 2 weeks from today. You know, I want you guys to take this serious, to really work on this. This is an important thing. It's a really good experience or opportunity to learn how to, this is kind of very real now, so it's a very good exercise, I think. All right, but yeah, that's basically it. So I think I covered everything. Yeah. That's it. All right, guys. Well, I guess that's it. We're gonna stop here for today, and please let me know if you have any questions.